Hello everyone, good evening. So today the link is active for review. Okay, so please do see your answers. Some of the questions were asked earlier, so we had uh, very few questions, but the parts of more than one questions from the same problem. Yeah, so as we have been doing in all homeworks and quizzes and all. Okay, so pattern was as earlier. So based on your feedback, I think there is a need to take this course seriously. So if you have any difficulty, general feedback, you can tell me now if you want. Any feedback on the exams?
Sir, actually, the thing is like uh, 35 questions, doing 35 questions in 2 hours is like only calculation mistakes happen, such kind of things. Like there is very shortage, feels like shortage of time because every like the same concept is applied on every question, but the calculations change. So,
Yeah, so that's why you should go slow. You at least solve a few questions, but solve it correctly. Being an engineer doesn't mean that you just know the method. You have to really apply and you have to find out the actual number. It's a very important. Otherwise, you are not an engineer. Okay. So even if you do just one, two questions, even then you can do better than targeting all of them, and at the end you end up making mistakes. Yeah. So see, in offline mode there is a way of doing things differently. In online mode, i'm not I will not give you the multiple choice question. So the type of question that we ask, you have to find out your strategy. This is known to you, like in homework also it is there, the same pattern, and in other quizzes also. So by now you should know basically. Yeah, and this is the same question for everybody. So I think it's not about calculations. There are a lot of which are straightforward. You can, yeah, partly what you are saying, the calculations are there. Of course, calculations are there in finite element analysis. Calculation has to be there. Yeah. So this is a numerical uh, course. Yeah.
so but the thing is like. Uh, like so, there is a human tendency to make mistakes in the calculations only. Like we cannot be 100% excellent in the calculations only. Like
No, I do not agree. Yeah, I do not agree. If you are, the equations, all those are finally comes back to equations. You can make mistake in one or two. You cannot make mistakes in all of them. Yeah.
yes, sir.
Yeah.
Yes,
So don't tell me that in all of them you make mistakes. So if you have formulas are correct, so then if you calculate using your calculator, you can make mistake in one or two. Yeah, and if it is reasonably within the tolerance limit, I also give you marks for that. If it is within
yes, sir.
1%, I give you marks. So, see, I think you have to accept that you have to be serious about this course. Otherwise, it will be difficult. Yeah. And because of the online mode, I'm not comfortable with giving the multiple choice questions. And this pattern is not for today. Okay. So quite a few students are there whom I thought like this must be the third course I'm teaching. So when it was offline mode, I have different strategy there, but looking at the cheating and all kind of things, I have to be careful. So I have to be fair for all students, especially those who are serious ones. I want them to study well, and they should be rewarded. Not like multiple choice, just guess and you get the marks. It will not serve the purpose. Yeah.
Yes, sir. Yes, sir.
Yeah. Just for your knowledge, there's also a student from computer science department, and he doesn't have any mechanical engineering background, but he has done really well in this exam. What about that? Yeah, they really appreciate who has learned, like taken courses of computer science only. He may not have background in mechanics and all kind of things, but still he is done well. So that's what I'm saying. I mean, you have to be serious about it. You have to, you read it, you solve the problems, or all kind of things. If you do, automatically it will come to you. And some questions, which I think 11 marks questions came from something which was there already in a quiz. Yeah, no? So even if somebody sees that how the solution is, you should know basically. At least 11 marks everybody should have got, no? Why did not happen that? Yeah, online doesn't mean that it's easy, so and this course is uh, like numerical is something very important for this one. This is numerical analysis only. Yeah, so if you know how to do it, you know the equation, and you are not able to apply it, then probably you have not learned this course. So anyway, you still have chance basically. So you have to be serious about it. I see even for homeworks, students are not giving their 100%. What we see is like very few are getting 100%. At least for homework, when you get a lot of time, I think you have to spend more time and work on it. Yeah. Any other comment? Yeah. Okay. Okay, guys. So I will share the project. Project details. Remember that you have two things very easy here. One is homework, that is 10 marks. Another is project, that is 10 marks. So 20 marks, anybody who is just serious, little bit serious, he can reasonably get out of 20, he can get quite a few marks, and then just getting 15 marks more to pass this course. So it's actually easy. Okay. So take the homework seriously, take the project seriously. Yeah, the project details I will share very soon. Okay, now we will start chapter 6. Yeah, and chapter 6 is about multidimensional problem. It's multidimensional. So whatever we have studied, we are going to extend is to multidimensional. So we have just X system here, thus X is varying. Now multidimensional means you have X, Y, Z system. Your domain was one dimensional or called 1D problem. Your domain is 3D. But 3D is extension of 2D only. If you know 2D, then you can do on 3D. 3D is little bit more lengthy, so we will actually devote time on 2D only. 2D only, 3D left on you. Left on you, you can work on it. If you understand 2D, you can understand 3D. You can formulate problems in 3D as well automatically. Okay. So 2D problems, okay, and 2D problems also have two kind of things. Yeah. So 2D problem also will have, okay, 2D is the domain. And domain means a plate, for example, 2D plate, right? You will have X and Y. This is 2D problem, right? Okay, but the problem, the values or these nodes may be a scalar or vector, right? So if you have a temperature, for example, temperature is a scalar, right? So if you have a heat transfer problem, then you call it a scalar value problem. Yeah, because T is a scalar, right? And for diffusion also, maybe this is a concentration, right? So T1, T2, T3, T4, for example, right? And then these are at this point the temperatures are, yeah. So all these variables are scalar value problem. Then there could be what we call it is the vector value problem. Yeah, and that will be, let us say you have a plate and you are talking about now the displacement. So you have ux1, uy1, ux2, uy2, ux3, uy3, ux4, uy4. See, every play, what you have two things, two values, right? So actually it's a displacement, but since displacement is vector, so this is vector value problem. So this is more difficult, yeah? So vector value problem, we will revisit chapter 9. We will take it up in chapter 9. We have to wait till then, okay? So we will look at if you have the plane stress problem, yeah, plane strain problem. So those have displacement at each node and it has two components. So we have to wait for that. We will, right now, we'll take what you call it, the scalar value problem, meaning that if the only one variable per node, yeah, and this is what we will study, and this is chapters 6 plus 7 plus 8. And it is organized the same way as chapter 3, 4, 5 are. First one will be looking at the problem itself. Second, on the formulation of what you call the trial functions, right? So the shape functions and all, yeah, type of elements and all that will be there. And chapter 8, you are actually solving the problem, yeah. So again, I'm saying that we will follow the same pattern what we did for in respect to chapter 3, 4, and 5. So we will go together. Basically, we will finish one type of chapter, then finish this, and then we have the next type of problem, and again we go from here to here. That way we can complete it. Yeah, so this is how it is. Okay, guys, I think the base thing first is to start with the 1D only. Okay, so 1D, we have to relate it with 2D, right? So if you do 1D problems for the heat transfer, right? So how did we start? We had one equation, something like this: d square t dx square. We had k here, plus we said x, sx equal to 0, right? So this is where we have a bar like this one, and then there is no heat transfer on this surface, right? Yeah. So this is insulated. So this surface is insulated. And then for that, we have this problem. So only at boundaries, there is a heat transfer there. Otherwise it is conducted, or it's a heat conduction problem. It's a heat transfer is actually heat conduction. Purely heat conduction problem. Yeah, so we have this one. And this is very simple to solve, as you know, like you can have t is equal to minus s over x k dx, right? And this is dt over dx equal to like this one, and further you can have t is equal to minus again s x k dx dx, right? And you can have on the whole domain you do it, you can find out the t. So this dx is very easy to find out, right? Yeah, so in this case, depending on what the value of s is, you can find out, as simple as that. So here there will be area as well, because this is 1D, so we also had the area here. So k over a will be there, and then you can do it. Yeah. Now, for this, we can find out the exact solution. Exact solution is you have to know, so that you can compare how the solutions are. So the next thing will be to look at the where it is not insulated, right? So this we have derived already. Yeah, so when this is not insulated, and there may be here the what you call it, the convective heat transfer. Yeah, so this is convective heat transfer taking place here. Yeah, so in that case, the equations is something like this. We have Ka, and then you have dt d square t dx square, right? And then you have minus, right? So we have minus t, let's call it alpha t, right? Okay, and plus beta, some beta value is equal to 0. So it will be something like this one. Yeah. Okay, so we get something like this one. You have t here, because what happens is you get a value here. Actually, we have derived already. Yeah, so we have derived already, and like it is we derive some sort of this d square t dx square, and plus, and we have t infinity minus t, yeah, then h, yeah, and then the surface area of that involved. So you have 2 pi r, something like that. Yeah, r naught is equal to 0. So this is, if you expand it, it will be this nothing but alpha, and this is also, in fact, it will be alpha. Okay, so beta will be this multiplied by this is beta. Yeah, so this is how this form is. And how will you solve? If you have this kind of problem, then how will you solve? First, you have to know the solution method. Yeah, and for that you have the already you have dot background. Yeah, so you have UG students here have background in differential equations. I think differential equation is mostly core course for all UG students. And for master's students, they have engineering mathematics. Yeah, so they must have taken that already. Okay, and for PhD students, of course, either they have done masters or undergrads, and they must have solved this course, because differential equation is the core thing for mechanical engineering. Without that, you will not understand many things. So how to solve if you have these kind of things? How to solve? So although it is 1D, we should have done earlier also, but I want to make a connection. Yeah, we are going from 1D to 2D. We want to look at how things will change as far as the exact solution is concerned. So exact solution you need to know, right? So okay, so what do we have? We have this equation. Which equation? We have Ka d square t dx square, right? Minus alpha t plus beta. Yeah, that's what that is, right? Okay, and that is equal to 0. Yeah, alpha is positive typically. You have that. Okay, now if that is the case, then how do you solve? You can, you first what you do is you do Ka d square t dx square minus alpha t equal to minus beta. You write like that. Yeah, and then you have two kinds of things. You have homogeneous solution, right? That is, there are two kind. Another is what you call a particular integral. So homogeneous solution, and for that you try to solve for this dka dts d square t minus alpha t equal to 0, right? You do this one, okay, and then here you how will you solve it? It all depends on the whether alpha is positive or negative. Yeah, and in this case alpha is positive. Alpha is positive in this case. Yeah, so accordingly you can look at, if this is positive, then what happens? This will be sinusoidal. If it is not, if alpha is positive, then the difference will be something else. So you also have something like same thing. You can write like this: Ka d square, right? You remember, minus alpha, right? T is equal to 0, and then you do d square. You solve it, right? D square is equal to alpha over Ka, and then d equal to root alpha over Ka. Yeah, and this root plus minus, yeah, this is a plus minus, and this is going to give you the solution, and that solution will be equal to the homogeneous solution. We are talking about Tx is equal to, right, you will have a naught a1, call it a1, or call it c1, probably is better. So c1 e to the power minus plus minus, so we have take one this and this, we write minus by minus alpha over Ka minus root alpha over Ka times x, right? And plus c2 e to the power root alpha over Ka x. So you have minus here, a plus here. Yeah, you can also write in terms of it. This is nothing but this kind of things also gives you the hyperbolic sines and cosines, right? You know that. So you know sine hx. Yeah, so you must be knowing better than me, you know. So you have done these courses, all those courses, and I did more than 25 years back. Yeah, so you should remember this. Now sine hx will be ex minus e minus x over 2, right? So x equal to 0, it will be 0, and then you can see how it goes, right? And cos hx will be equal to ex plus e minus x divided by 2. So this is how you are defining, right? And similarly, the tx, you can also write, tx will also be c3 sine hyperbolic root alpha kax plus c4 cos hyperbolic, right? You can write like that, right? So cos hyperbolic root alpha over kax, and automatically this case takes care of that, because sine and cosine, both of them has this plus x and minus x. Yeah, so finally it will work out and become like this also. So either you can express like this hyperbolic sines and cosine, or you can have like something like this one. Yeah, all this is a repeat of what you have done. This is not even in your book probably. Yeah, so I'm just making sure that you have this revision, so that you can know that what is the exact solution and how your finite element solution is differing. Yeah, remember that. Okay, now next thing is this is a homogeneous solution. And what is the here? What is the next one? This is minus beta. Beta is constant, right? So given typically the particular integral has the same form as the whatever is there on the right side. Yeah, so here the beta is constant. Typically, the solution of particular integral will be a constant only. So we will say particular, let us say particular integral is dx is equal to a constant. Yeah, so let's call it's a gamma is a constant, right? So we have a ka, then we can have this equation, right? Ka ds square t dx square minus alpha t is equal to minus beta, right? So equal to minus beta. What we are going to do, we'll put tx equal to gamma here. And what do you get? We get Ka, and this square double differential of that. This is a constant, so it becomes 0, right? So this becomes 0 minus alpha t, where t is also equal to gamma is equal to minus beta, right? So what do you get? So you get this becomes 0, and you have minus cancels out. You get gamma, right? Gamma equal to beta over alpha. So gamma is equal to beta over alpha. That's it. Yeah. So what is your solution? Solution is the combination of both of them. So what you get the solution is dx is equal to c1 e to the power minus root k over alpha x plus c2 e to the power root ka over alpha, right? And then plus beta over alpha. So this is your solution, right? So this is the how, and then you can apply the boundary condition, right? The C1, C2 you can find out based on what is the boundary condition. You have the C1 and C2, two variables unknown. There will be two boundary conditions. You can find out value of C1 and C2. As simple as that. Any question, guys? Any question? Okay. And similarly, there could be some other kind of problem. According, you can find out like you may have advection problem, right? So advection, diffusion advection, or actually it should be diffusion advection, you call it. Problem. And you have seen in that case that you have terms of this as well. So you have what you call diffusivity dA d square c dx square minus, there is a velocity term here v, right? And then or we have discussed this earlier, so it's nothing new. So you have v, and then you have dc over dx. Yeah, so we have the dc over dx, you can have that, and then there will be the source term sx equal to 0. So it could be something like this. Yeah. Okay, now if that is the case, then what happens? There may be a here also. Okay, so I think there may be a because of that. So we multiplied by a. Okay, now if that is the case, then how to solve it, right? So then you will have dA. You see, dA square c dx square minus BA dc over dx is equal to minus sx, right? And then what we see here is the first you have to look at the homogeneous solution, right? So homogeneous solution, and what you get is here d. Okay, I already wrote d here, so we have to be careful with the actual d that we write, like d like this one. But doesn't matter. If you have this kind of thing, then you can also use other methods that you may be knowing. So okay, so not necessarily you have to follow this one. Now what we have, so let's use this this del as d over dx term. Yeah, so accordingly what we get from here is dA del square, right, minus, right, del square c, right, and then VA, then del C is equal to 0, right? And what we get here is D, so C will be here, and here we have dA del square minus VA del. Yeah. Okay, C equal to 0. Yeah. If you do that, you will get two terms here. So I mean, if you solve it, one will be del equal to 0, because it will be del equal to 0, and then another will be the dA del equal to, so dA del minus VA minus VA equal to 0, or del equal to VA over dA, right? So what do we get? We get some equation which will be like this. So accordingly, your equation will be something that it goes like this. So Cx will be equal to now C1 e to the power, you have 0. So basically it becomes a constant term basically, right? So it becomes a constant. So C1 and then 0 times x basically. So you can interpret that way as well, plus C2 and then you have VA over dA. So anyway, A will cancel out, let us say, and e to the, sorry, that will be E term here times x. Yeah, so it will be simply C1 plus C2 and e to power b over dx, right? So Cx will be of this form, for example. Yeah. So you can put these values there, you can see, and you will see that actually it will follow the same thing. Yeah. So this is how this will look like. Yeah. And now the depending on the value of Sx, you can also find out the particular integral for that. Yeah, so you can also put the, if it is a linear, if it is a constant, for example, you can put a constant value and see. Yeah, so and if it is a linear value, a plus the bx, you can put the similar value here and see, find out what the a and b is, and you can solve it that way. Yeah, so this is how you do, right, regarding this. Okay, now any question so far, guys? This is not something we are doing new. Okay, and in fact, before you do this course, you are supposed to know all those things, but still I'm repeating. Yeah, so that you are clear in your mind. Yeah. Okay. Now, only thing is, what about the 2D? Yeah, 2D problem. What is new? First of all, what is the equation itself to begin with? And that we should know today. Yeah, so what is the equation? Okay, now let's look at the equation of the 2D problem. Okay, once you know the solution for 1D problem. Yes, Subham.
Sir, by mistake.
Okay. So, yeah, you have a plate. Let us say thickness is T is equal to 1. Yeah, this is the thickness we are talking about. Yeah, so unit thickness it has. Yeah, and which all things are there? We have maybe, we write thickness somewhere else. So write thickness equal to 1. Yeah. Now we have a Qx here. Yeah, Qx, right? And this will be Qx, right? So qx plus, we can also write in terms of, let us say qx, this value has qx and qy, right? And this value is dx and this value is dy. This is qx here, so you are coming this way, so you can write qx minus, so you can write qx minus del qx over dx multiplied by dx over 2. So basically qx plus dqx over dx2 dx multiplied by minus dx over 2 is the same thing, right? And this side, this is a qx plus, right, plus dqx plus dx multiplied by dx over 2, right? So this is these are the flux basically, right? Here these q's are, remember these q are flux now, qx and q are flux. Yeah, these are flux. So we have to accordingly, when we have to do the balance, energy balance, we have to multiply this with the area here. Yeah, so in 2D we have this as a flux. Okay, now similarly for y direction, we have qy in the middle. Yeah, so here we have qy, right, minus, yeah, dqy over dx, sorry, dy over 2. Basically how it comes, if you wonder, this is the qi plus, you can also write dqy over dy multiplied by minus dy over 2, right? This is the same thing, right? So this, and you are coming down, you know, so we have from here we are coming down by dy over 2, and hence you are writing minus here. Okay? And here you have qy plus dqy over dy multiplied by dy over 2. Yeah, and then there could be a source term sx, and sx will be per unit area. Yeah, sx will be energy source, right? This will be watts per unit time. Yeah, so sorry, watts per unit area. Yeah, so w per meter square will be the unit for that. Yeah, because it's a 2D problem, so we will write that way. Now once we have that, then there has to be energy balance, and we are going to do that now. So you know that the heat is conserved. Okay, and this is a steady state problem. Means whatever things energy comes, that has to leave. So total energy is equal to 0. Yeah, total heat gain by that element is equal to 0. Hence we will take incoming energy as positive, and hence you see which all things are incoming. These are incoming, this is incoming, this is incoming, these are outgoing, these are outgoing, right? So you write this plus this plus this minus this minus this, you write like that. Yeah, and we have to multiply by area also, right? And all of them will have area. So we will start with incoming left side, and we have a qx minus dqx over dx, yeah, multiplied by dx over 2 multiplied by, this is this term we are talking about, but this is dy, and the depth is 1, so just dy multiplied by 1. So we have dy multiplied by 1, right? Okay. So this is incoming. Outgoing will be in the x direction only. We have qx plus dqx over dx, dx over 2 multiplied by dy, right? Okay, so this one is for the right side. Similarly, we can do for this and this as well. So we have plus qy minus dqy over dx, right? Okay, I think we some made mistake. It has to be dy. Okay, so remember this is no, I think it's okay. No, fine, dy is there. Okay, so here dy, so this will be dy, okay, multiplied by dy over 2 multiplied by dx multiplied by 1. So what? This multiplied by this length multiplied by 1. Yes, total area we have to do. So this is positive, and then we have minus qy plus dqy over dy over 2, right? And then dx multiplied by 1, right? Okay, and then sx multiplied by the area of this one, dx and dy both. Yeah. So dx and dy, right? Multiply by 1 also we can do. Anyway, this is giving for per unit area, assuming that the volume is the depth is 1. So it is the same thing. Either you can multiply by 1 or so. This still it has per unit area. Okay, so now this is equal to 0. Yeah. Accordingly, you can see which all things will be cancelled here, right? So if you see here, this and this will be cancelled, right? This is minus here, and similarly you will see that the qy and this will be cancelled, right? And the rest, if you see, you see dx and dy is there, dx and dy is there, half coming from here, half coming from here, so both will be this minus, this becomes minus dqx over dx multiplied by dx dy, because half will be 1. Similarly here, this will be minus, this also becomes minus here, and half from here becomes dx times dy, and plus becomes sx dx times dy. So what equation we get? We get simply minus d over, okay guys, so I think here we should have used a partial derivative. Yeah, so here actually partial derivative, so we made a mistake. I should have done that earlier. So remember, all these are partial derivative. Okay, so these are partial derivatives. Why partial derivative? Because this is this has two variables, so it is not okay to write like that. Okay, but I'm correcting it here, so please correct in your notes. So this becomes minus del, right, qx over del x, right, and then you have dx dy, then you have minus del qy over del y, right, then dx dy, right, plus you have sx multiplied by dx dy is equal to 0. Finally you get that, or all dx, right, so dx times dy. Okay, so that can be removed now, and what you get is minus del qx del x minus del qy del y, right, plus Sx is equal to 0, right? Or you can write minus, also you can write minus del dot q plus Sx equal to 0. So this is a vector form, vector notation, where this is nothing but the gradient. You call it the what is this one? This is a divergence, not gradient, divergence. This is divergence of q. So q, this one is where del is equal to nothing but del over del x I plus del over del y j, right? And what is qx? What is q is equal to qxi plus q, divergence of that. So you can, so basically del dot q is equal to divergence of q, right? So this is the vector notation. Also you can write the matrix notation as well, matrix notation. And in matrix notation you have the delta dot, right, delta dot q, right? So this is in bold basically. Remember, so this is typically you write in bold, yeah, because these are matrix, yeah. So this is equal to nothing but delta t q, yeah, where maybe you write wave like this, so this is matrix notation where delta wave is equal to del over del x, del over del y, yeah, right? And q is equal to qx and qy, yeah. So okay, so I think this should be something like, no, there is something wrong, we will not write like that. So where this is equal to like this, del over del x, del over del y, and q tilde is qx and qy, yeah. And so that del tilde transpose q transpose, which we are saying is equal to the divergence of q is equal to nothing but del over del x, del over del y, and then you have qx and qy, right? So you have this multiplied by this. So you write in vector notation like this one, yeah. So but regardless of how you express them, your equation remains the same. The equation is divergence of q is equal plus sx is equal to 0. Now this is what is coming from the energy, right? This is coming the conservation of energy. Now here q itself has to depend on temperature, right? We are solving this is a heat transfer problem, so temperature has to come. And how does it work? Then you have the Fourier law, right? Fourier law. And what Fourier law says? It says qx is equal to minus k dt over dl. Sorry, k del t over del x. And similarly, qy says minus k del t over del y. Of course, this one is for the isotropic material. This is the heat conductivity. If it is isotropic, then this is how it is. So assuming the isotropic material, our qx, your qx and qy, we can write it as minus, we can write here is equal to minus del t over del x times k minus k del t over del y. Or we can also write it as k 0 0 k, right? And then we have this del t over del x and del t over del y. We can also write like that. Yeah. Okay. This one is a matrix, and then you have this like this one. Yeah. So how do you write then? This one is nothing but this is q, what we wrote as q tilde is equal to let's call this a D matrix, D tilde, and then you have what is this? This is gradient of t, right? So this is del t is gradient of t, right? So where this delta, we called it okay, we wrote it differently, so we write like this: delta tilde and t. Yeah. Okay. This is in matrix form, like this one, but we have negative here, remember, so we have negative, so we write negative here like this. You can also write here, we have, if it is like this one, then we can write it together basically, right? So here we qx and q, you can also write in terms like this. So q, right, is equal to this, equal to like okay, this is from here only. So this one is qx, and the q is nothing but, the q as a vector form is nothing but qx I plus qyj, right? You have like that. Okay, so that means this is, when you write qx qy, the q itself is equal to, you can expand it here. Now qx is nothing but this minus k dt dx. So this becomes minus k dt. Okay, so pardon me, here del t over del x. Yeah. So we are writing this one, minus k del t dx minus k del t dx I, right? Then minus k del t del y, right, is equal to minus k, and then what we have, del over del x I plus del over del y j times t, right? And which is equal to minus k, and then what is this? This is nothing but this symbol, right? So this is this, and then t. So what is minus k, and this, what is that? We have gradient of t, right? So gradient of t. Yeah. So what is the equation? Finally, the original equation was, if you remember, minus, we have this dot, so we have divergence of q plus sx is equal to 0. Now you have q itself, which is a function of t, which is minus k, and then we have the gradient of t. So we can write minus del dot minus k gradient of t plus sx is equal to 0. Yeah, so minus minus becomes plus, or you can write gradient of k, divergence of k times gradient of t plus Sx equal to 0. So this is what the equation is. Where this del vector is equal to del over del x I plus del over del yj, right? So this is what that is. Yeah. So this is the equation, and then you can solve it. Yeah. You can also simplify it. Yeah. So finally, you have to simplify it, right? So let us say Sx equal to 0. We will see the scenario, right? So if it is Sx equal to 0, then what you have? You have del dot k del t is equal to 0, right? So you can have del over del x I plus del over del y j, right? Dot. Let's say k is constant, so k will be here. Then you have del over del t over del x I plus del t over del y j is equal to 0. What you get is k del square t over del x square plus k del square t del y square is equal to 0, or k del square t is equal to 0, or simply you write del square t is equal to 0, which is also known as Laplace equation. Yeah. Okay, so finally what we found, for the simplest case that there is no source, this is simply a Laplace equation. Now the problem is, now you have to think about, and we will see tomorrow, that what is the solution of a Laplace equation, how to solve it. Yeah, so you have to know how to solve it, right? Then only if you have to be convinced that you cannot solve a problem using a conventional known method, then only you attempt the finite element method, right? So you have to know that what is the solution of a Laplace equation, or meaning that you can see this is the Laplace equation, or simply del square t over del x square plus del square t del y square equal to 0. What is the solution of that? Just think about it, just recall, and then we will solve this tomorrow. Any question, guys? Okay. If there is no question, yeah.
Sir, in Q, do we have like the shear type component?
In Q,
I mean, heat flux or this type. Although they
yes,
won't matter, but
yeah, there is one actually. It is actually it is. In D you are talking about, right? So in D there will be some. So this is for like if the material is not isotropic, in that case there is something there. So for an isotropic material, so in that case you have D is equal to, you will have kxx or kxx, kxy, kxy, kyy, like that. Yeah. So you can have this kind of problem. So that really means when we are talking about this equation, right? So qx and qy will be given by D like this one. So instead of k here, this will be kxx, kxy, kyx, kyy here. Yeah. So that term will be there, but for isotropic material that is not there. Yeah, got it?
yes, sir.
Okay. Any question, guys? Any other questions? So you can write qx, qy is equal to minus kxx, kxy, kyx, kyy, and then you have del tx, del ty, like that. This is an isotropic material. Any other question, guys? Yeah. Okay, if there's no question, see you guys tomorrow. Okay.
Thank you so